again, so last time we were talking about time reversal invariance and what is time reversal symmetry of a system. It changes the momentum from p to minus p and lets the system evolve in time, and if it retraces its original path, then you say that the system has time reversal invariance. And we also showed that when a system has time reversal invariance, then the time reversal operator is actually an antilinear operator, which is given by u times k. And what we mean by antilinear also, let me just specify it. T is an antilinear operator that is T operating upon A phi 1 plus B phi 2 will actually give me A star T phi 1 plus B star T phi 2. So, because it is taking the complex conjugate of A and B. Now, let me see what happens in the case of spin orbit interactions. So, if we have spin orbit interactions, then what happens is that your spin orbit Hamiltonian is given by sigma over I, some function of Ri times Si dot Li. Since Si and Li both are angular momenta, under time reversal Si goes to minus Si and Li goes to minus Li, because Li is nothing but Ri cross Pi. So, Pi goes to minus Pi, so it goes to minus Si. Therefore, time reversal invariance is retained. In fact, the only time reversal is lost is when the Hamiltonian is complex, and the Hamiltonian is complex when you apply a magnetic field. So, in the presence of a magnetic field, time reversal invariance is lifted, otherwise time reversal invariance is there. Now, let us see in this case, of course, you know that psi of Ri is given by h cross squared by 2 mc squared times 1 by r del v by del r, where V is the potential. Now, let us see whether what should be the form of the time reversal operator. Time reversal operator in case of spins cannot be just k. Why is that? Because when I take a spin half particle, then you will see that spin half particle operators for Sx, Sy and Sz angular momentum are the following. The matrices for Sx, Sy and Sz are given by the following, that is Sx is equal to h cross by 2. These are all 2 by 2 matrices. So, this is 0 1 1 0 and Sy is equal to h cross by 2, 0 minus I 0, and Sz is the matrix h cross by 2, 1 0 0 minus 1. So, what you see here is that except Sy, the other two are real, the other two matrices are real. So, if I take a complex conjugation, then you see the following, that is Ksx is actually equal to Sx, Ksz is actually equal to Sz, and only Ksy is equal to minus Sy. So, only Sy changes sign. So, if you want the entire angular momentum to change sign, which is what is required in time reversal operation, what we need is the following, that is, we need to change Sx to minus Sx and Sy to, rather Sz to minus Sz when T operates. This is possible when you take the system and rotate by pi by 2 around the y axis, that is, you have x, y and z. So, if you rotate around the y axis, then by pi, not pi by 2, when you rotate by pi, then x goes to minus x and z goes to minus z. So, if the spin operators are rotated by pi about the y axis, then Sx goes to minus Sx, Sz goes to minus Sz, and Sy stays as it is. So, which means that the form of the time reversal operator for spin half is the time reversal operator S is equal to half is actually T is equal to complex conjugation multiplied by e to the minus I pi Sy by h cross, and this will give me e to the k times e to the minus I pi by 2 times sigma y by the definition of the Pauli spin matrices sigma x, sigma y, sigma z, and their relation to the spin operators Sx, Sy and Sz. Now, let us see whether we can simplify it further. So, I have T equal to k e to the minus I pi by 2 sigma y, or I can write it as k into cos minus pi by 2 sigma y minus I sin minus pi by 2 sigma y. Now, we can expand. So, this is actually sigma y comes inside the argument of the sine function and the cosine functions. So, what we can do is we can expand cos x sigma y can be the following: 1 minus x sigma y by 2 the whole squared minus plus x sigma y to the power 4 upon 4 factorial minus x sigma y to the power 6 upon 6 factorial plus minus etc. etc. So, what we know in this case is that sigma y has the property that is a Pauli matrix, and Pauli matrices have the following properties. We have sigma y squared is equal to 1, so also our sigma x squared equal to 1, sigma z squared is equal to 1. So, if we introduce that, then what we will find is the following. We find that cos x sigma y is equal to 1 minus x squared by 2 plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial, etc., etc. And similarly, we can have a sine function has the following expansion: sin x sigma y is equal to x sigma y minus of sigma y cubed x cubed by 3 factorial plus sigma y to the power 5 x to the power 5 by 5 factorial, etc., etc. And we can use a fact that this is equal to sigma y times, okay, so this I can actually say is nothing but cosine x. So, I can have this one as sigma y x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus plus, etc. Sorry, this should have been minus. And this will give me sigma y sin x. So, what we have is e to the minus I pi by 2 sigma y is equal to cosine pi by 2 minus I sigma y sin pi by 2, and this gives me just simply minus I sigma y. That is it, because sin pi by 2 is 1 and cos pi by 2 is 0. So, having gotten this, what we have is that time reversal operator for spins is minus I k sigma y. K is the complex conjugation and sigma y is the Pauli matrix. And we also have the following, that is, if we have n spin half particles, then the time reversal operator is nothing but t equal to pi over I equal to 1 to n, let me call it j equal to 1 to n, minus I sigma j y k, and this will be minus I to the power n k to the power n pi I pi j sigma j y or this is equal to minus I to the power n k to the power n sigma to the power n minus 1, I mean rather n not n minus 1, sorry, n y, and if n is odd, if we have odd number of particles, then t is equal to minus I k sigma y, because k to the power 2n plus 1 is equal to k sigma y to the power 2n plus 1 is equal to sigma y, and so forth, and minus I to the power 2n plus 1 equal to minus I. If we have an even number of particles, then t is equal to I to the power 2n, and that is 1, and k to the power 2n is 1, sigma to the power 2n is 1. So, just t is equal to 1, and we can also say that we also find Therefore, T squared is equal to 1 for even number of particles and T squared is equal to minus 1 for odd number of particles. It is in fact the later one that is very important. We also have one more result, that is, supposing if psi comma phi is the inner product of two functions psi and phi, then T psi comma T phi is equal to psi star comma phi star is equal to psi comma phi star or is equal to phi comma psi. So, this is another important result. Now, let us see what happens when we are looking at spin half systems. So, we know two things. One is that if psi is an eigenfunction, with energy E, then T psi is also an eigenfunction with energy E. So, let us see what is the relation between T psi and psi. T psi comma psi, if I take the inner product, what I will find is the following. I can take this to be T psi comma T squared psi by using the above result, that is T psi comma T psi is equal to T psi comma T phi is equal to phi comma psi, and this is equal to T psi comma minus psi, because T squared is equal to minus 1 for odd number of spin half particles, for an even number of spin half particles, of course, T psi comma psi is equal to T psi comma minus this thing. When you operate by T, then nothing changes. So, now what we have is, therefore, we have the following: T psi comma psi is equal to minus psi comma T psi, or T psi comma psi, same thing. So, this is possible only if T psi comma psi is 0. This implies T psi comma psi equal to 0, or T psi is orthogonal to psi. So, when two states T psi and psi are orthogonal and have the same energy, this implies that the state has two-fold degeneracy. So, whenever you have an odd number of particles and you have time reversal invariance, then the system must necessarily have at least two-fold degeneracy, because T psi and psi are orthogonal. So, this degeneracy is called Cramer's degeneracy. Cramer's degeneracy, and the two states are called Cramer's doublets, and the states are Cramer's doublet. Okay. Now, So, we know that whenever we have a odd number of particles or just a single particle in the system, then if it is a spin half particle, then there is necessarily a two-fold degeneracy. Now, let us go from here and see what happens in the case of band states. So, coming back to energy bands, is basically a one electron theory. So, my state e to the ik dot r uk is an eigenstate of a single particle, eigenstate of a single particle with spin, that is an independent particle state. Okay. So, with spin, or in other words I can have a psi k up, I can say, which is, so here I can actually write down up is an eigenstate of single particle with spin up. So, I have psi k up is equal to e to the ik dot r uk up or uk alpha, whatever way you want to call it, because up is also means alpha spin and down means beta spin. So, it is one and the same. Now, what happens? If I operate on this by T psi k up, this is equal to minus I sigma y k operating upon e to the I k dot r u k of r times up. So, this will give me k operating upon e to the I k dot r will give me e to the minus I k dot r, and then I have minus I sigma y operating upon, and I can also write down u k r right here, because that is a, I can take that wave function to be real without any loss of generality, and I have minus I sigma y times k operating upon spin up. So, minus I sigma y k is actually something that rotates, actually it is only minus I sigma y, because k is already operated on because the spin up or spin down does not have a I. So, this is nothing but e to the minus I k dot r u k of r times spin beta, because that operator minus I sigma y actually rotates the spin by pi around the y axis, and what I get is spin beta, or I can write this down actually as the u k, now I can say is minus k, because I have e to the minus I k dot r there. So, I can write it as e to the minus I k dot r, the label on k changes to e to the minus k r times down spin. Okay. Now, u minus k r is also an eigenstate of the k dot p Hamiltonian with the wave vector minus k. Now, what does it mean? It means that T psi k up, there is a degeneracy between psi k up and T psi k up equal to psi minus k down. So, we have the following result, that is E k up, which is the eigenvalue of the state psi k up, is equal to E of minus k down, which is the eigenvalue of the state with k vector minus k, and degeneracy between T psi k up and psi k up. I should not say equal to. So, this is very interesting, that is the time reversal symmetry imposes degeneracy between states of opposite momenta and opposite spin. Usually in atomic or molecular physics, what happens is that in the same orbital you will have the degeneracy between the up and the down spin because of time reversal. In this case it is not so, it is in different crystal orbitals where the degeneracy occurs. So, for example, if I plot my energy band picture, what I will have is the following, that is E versus K. So, if I have this is the energy of the K up state, then the energy of the K down state will be like this. So, this is the minus, this is the upspin state and the downspin state. I don't put the labels K up and K down, but I only up and down. This is upspin and this is downspin. So, you will see that there is a degeneracy between the states with a K up and a minus K down. So, the degeneracy is not at the same point in the Brillouin zone, but at diametrically opposite points on the Brillouin zone for the up and the down spins. So, this is quite important. Especially in the context of the modern day topics like topological insulators, important in topological insulators. Where the backward scattering of electrons on the delocalized edge states is forbidden due to spin reversal. That is, unless you have a magnetic impurity, any impurity cannot scatter a state which is K up to minus K down. You require a magnetic impurity to scatter the state from K up to minus K down. So, this is important in some of these physics. So, what I will do after this is, in the next lecture we will discuss what happens when you have the inversion symmetry, and then you have spin orbit coupling and inversion symmetry. That is, there is time reversal, there is spin orbit interaction, and then there is inversion symmetry. And then in that case what happens to the energy bands. So, we will discuss that in the next talk. Thank you.